Welcome back. I'm now going to actually do a couple of more rates of change problems because I think the first one I did was probably a little bit more complicated than I wanted, and it actually the hard part was actually the geometry, not the calculus. So let's just say I drop a rock into a pond, and it has a ripple, and the ripple spreads out. It'll probably have multiple ripples, but let's just say we focus on one ripple, and the ripple is spreading out. So let's say, so let me draw. This is where I drop the rock, right? And then this is the ripple in the pond. It would be an actual circle, which isn't what I drew, but close enough. Okay. So let's say that the ripple, so let me say that, let's call R. R is not for a ripple. R is the distance that the ripple is from the center, from where it started from the get-go, right? And it's not by chance that that's also for radius. So let's say that the ripple is moving out at 2 meters per second. So the rate at which R is changing with respect to t is 2 meters per second. And what I want to know is, what is the rate at which the area of this that's kind of included by this ripple, right? What is this entire area? How fast is that changing with respect to time when the ripple is, let's say, 3 meters from the center, when the ripple is equal to 3 meters. Well, do we know any relation between the area of this circle essentially and the distance of the ripple or the radius? Well, yes, we do. Area is equal to pi r squared. And so we want to figure out the rate at which area changes with respect to time. So what does the chain rule tell us? The chain rule tells us that the rate at which A changes with respect to t is equal to the rate at which A changes with respect to r times the rate at which r changes with respect to t. Well, we already know this piece, right? We already know the rate at which r is changing with respect to time. That's right here. So all we have to do to figure out the rate at which A is changing with respect to time, right? That's this one right here. Is we just have to figure out the rate at which A changes with respect to r. Right? Well, that's just the derivative. The derivative with respect to r. So we just say the derivative with respect to r, do it of both sides, of A equals the derivative with respect to r of pi r squared. So we get dA dr is equal to, what's the derivative with respect to r here? Well, that's easy. Just 2 times pi r to the 1. So we'll just leave it there. So that's pretty interesting by itself, that the rate at which the derivative of the area formula really is what? This formula by itself looks interesting, right? That's a formula for the circumference of a circle. So the derivative of an area of a circle with respect to the radius is a circumference. That is mildly fascinating. And something even more interesting is to figure out what the integral is figure out what the antiderivative is of the area, and compare that to the volume of a sphere. If you can look it up on Wikipedia or something, and you can, even look and compare that to the surface area of the sphere, and just keep taking derivatives and integrals, and there'll be some pretty interesting relationships. But anyway, back to the problem, not to go on too far of a tangent. So we figured out the rate at which A changes with respect to r. So going back to our original thing, we now know that the rate at which A changes with respect to t is equal to the rate at which A changes with respect to r. Well, that's just right here, right? The rate at which A changes with respect to r, well, that's just 2 pi r times the rate at which r is changing with respect to t, right? Well, the rate at which r is changing with respect to t is just right here, right? 2 meters per second. We figured that out. So 2 pi r times 2, and I won't include the units because that might confuse you right now. So the rate at which A is changing with respect to t is 2 pi r times 2. Well, are we done yet? Well, no, because we haven't substituted yet for r. So what is r? Well, we know r is 3 meters. So dA dt is equal to 2 times pi times 3 times 2. So what is that? 2 times 3 is 6, times 2 is 12. 12 pi, and it's meters squared per second, right? Because it's the rate at which area, square meters, is changing with respect to time. And if we multiply out the units, we would have gotten the same thing right here. So in the next video, I'm going to do a slightly harder rate of change problem, just so that you see that it doesn't only apply to kind of purely geometric things. It applies to pretty much anything that you can find a relationship between two values. See you in the next module.